Hello, good afternoon everyone. I'll be recording the chapter 2 of our discussion, and I'll be uploading this one in our YouTube channel. So as part of our asynchronous class, I will give you the link for this one, and then you will have to answer the quiz in our use step, and you can review this video. So that's really actually very good because you can be able to review the chapter 2 discussion, which is the topic is all about systems. So let's start with the discussion, and I'll also be giving you a time to be able to finish the quiz, which is until Saturday. Okay, so you will have a longer time to answer the quiz. And I will also be uploading a video for our chapter 3. As I've mentioned, I'm on leave. So I will be on leave for 2 weeks, and I won't be able to have a synchronous class with you. So I hope that you can be able to really um, have the time to check our YouTube channel so that you can um, take our chapter 3 quiz, which is also in you step. Okay, so there's no worry. I will be giving you 1 week time, 1 week of 1 week of a longer time actually to be able for you to answer your quiz. So for the chapter 2, I will give you until 2 to 3 days to finish or answering the quiz. And then for the chapter 3, you will have at least a week to answer the quiz for the chapter 3. So this video is for the chapter 2, okay? So let's start. This is all about system. So what is a system? Actually, if you read the book, it's this definition is actually a process or a combination of processes that take signals as the input and produces signals as the output. Okay, so a system wherein there is a combination of processes from input to output. So in example, in the book, it's actually like taking an audio input and produces its amplified version. Okay, so kung mang disco mo or if you go to any events, actually they need like an amplifier, right? Because um, if you wanna have a party, and you need to have a louder ano tingog, no? If you want to have a music, you want to have it louder. That's why you need an amplifier. So what is the input if you want to use an amplifier? Then the input would be an audio input, and the output would be an amplified version of that one. Another example is in image processing. No, in digital image processing, like even in your phone, there's actually a system in there wherein the input is a digital image, and the output is actually the filtered image. Okay, so there's already a lot of applications in our phone where this kind of systems actually already in place. Okay, so if you have a continuous time input, if you have a continuous time signal input, then the output would be a continuous time signal output, right? So it's called a continuous time systems. So this is the figure for that one. Okay, so this is our figure for a continuous time system. So also with the discrete time system, the input signal can be a discrete time signal, and the output can be a discrete time output. Yeah, so that's how you call it a discrete time system. Okay, next would be the interconnection of systems. So what do you mean by interconnection of systems? Normally, one big system is consist of different kind of subsystems, okay? So one big advantage of doing things this way is that it's easier to model and analyze smaller systems than larger ones, okay? But do you understand when you model and analyze smaller systems, it's not really that complicated, but the bigger ones, bigger systems are actually much more complicated. That's why you'll be using subsystems for that one. Okay, so that's why there is an interconnection of systems, right? So one example of an interconnection of system is a series or cascade connection, wherein the output or the input of the second system is from the output of a first system. Okay, so the equation for that one is y of t is equal to h1, which is the system 1, x of t multiplied using the asterisk h2 x of t. Okay, so that is what you call the series or cascade connection. Okay, and it is the simplest type of system connection. Second one is the parallel connection, wherein they have the same inputs. Okay, so for system 1 and system 2, they have the same inputs, which is x of t, but they have different, most likely, yeah, they have the same output. It is assumed. Okay, so for this one, most likely they will have the same corresponding output. Okay, so that is assumed. Okay, so the example for the equation is y of t is equal to h1x of t plus h2x of t. Okay, so the third one would be the feedback connection. So what is the feedback? Okay, so whereas in feedback connection, a portion of the previous output is fed back to the system along with the current input. So from its term feedback, no, the input of the system comes from the output, no, of that said system. So if you check this equation, um, from the x of t, which is the input, and it goes through a process in system 1, which is h1, then it already has an output, which is yt. But for the second but for the second time, it has a different input, because it goes through the second system, and that can become the input for the second process. Okay, so this is the um, feedback connection. Okay, so this is the equation. I'll just read this one. This is actually a self-correcting mechanism when the output of the system diverts from the. Okay, so this is actually used in the factories or in quality assurance. Okay, so once there is an error in the system, it will actually feed back directly. Okay, so then it will actually autocorrect whatever is wrong with the system. Okay, so that is this one is most likely used in the factories, or even in um, um, huge systems, right? Because it ensures that the output is um, ensures that the output rises or falls back to the desired range automatically. So hence, when there is a feedback, it can be a negative feedback or a positive feedback. Okay? And these are actually the equations for the positive feedback and negative feedback. So for the positive feedback, you just change that into plus, where y of t is equal to h1 x of t plus h2 of y of t, because y of t becomes the output, and this actually becomes the feedback from the first system. And for the negative feedback will be changed to negative. Okay, so you have to familiarize with that one. The third is the properties of system. Okay, so in this section, we introduce a couple of basic continuous and discrete time system properties. Okay, so for a system, for a system to be memoryless, its output at any instant depends only on the input at the same instant. Okay, so it's called memoryless systems, which are actually independent of inputs and outputs in the past or the future. So an example for the equation or the function for that one is y of t is equal to x t minus 1. So this in this kind of system, the output of the system at t is equal to 2, actually, or y2 depends on the input at t at time is equal, or t is equal to 1. Hence, x becomes 2 minus 1 or x1. So this system has a memory. Okay? So feedback systems actually excuse me, are actually discussed, no, but not in this chapter. So next is about causality. So a system is said to be causal if the output at any instant depends only on the values of the input at the present instant or past instant. So a while ago we were talking about sa ganito, we were talking about the memory of the system. So normally there is really a memory in a certain system. Okay, so that's why in the example that we had, the system has a memory with the actual equation, which is a y of t is equal to xt minus 1. So with that said, there is actually the system has a memory, which wherein at t is equal to 1, your x is actually 1, right? So in relation to being causal, it says that if the output at any instant depends only on the values of the input, that becomes causal, no? Meaning, this kind of output only exists if this kind of input exists, no? In other words, the causal system does not anticipate the future values of the input, meaning it does not really need. It means that, it needs that this kind of output will only produce, or will only be produced if this kind of input actually exists in the system. Okay, so an example for that equation is y of t is equal to xt plus 1. Okay, so in this system, the output of the system at t is equal to 2 actually depends, um, or y2 depends on the input at the time t is equal to 3. Okay, so this kind of system is non-causal. Okay, all real-time physical systems are causal because time only move forward. Okay, so sa example niya ganina, this one is actually not causal. Okay? Atong i-highlight daan. So, this equation, y of t is equal to xt plus 1 is not causal type of system. Okay? So, maybe, um, in my quiz, I'll show you a type of an equation, and then you'll have to tell me if it's a memoryless, if it has a memory, if it's a causal kind of system. Okay? But it is said that all real-time physical systems are causal. Okay, so you have to really um, check, no, because only our time only moves forward. Okay, so that's why all real-time physical systems are causal. Okay. Next is time invariance. A system is said to be time invariant if the system behavior doesn't vary with time, no? So such systems are expected to produce the same outputs for the same inputs applied at a different time. So may pasabot ana. So in this example, so in this kind of system, with the equation yn is equal to xn, this is a type of an invariant system since the input delayed by 1 second produces an output delayed by 1 second also. So you can see, um, this kind of system, if you can see, a shift in the input signal should produce the same shift in the output signal. Okay? So, kung ang causality or ang causal type of system is kung unsa, whatever your input at the present time is actually, there is a same output in that actual time, si time invariance means if there is a delay sa imong input, there is also same equal delay sa imong output. So that is time invariant systems. Okay? So next is stability. So a stable system is one in which small inputs does not lead to erratic responses. Okay? That doesn't grow out of control. So from its term, stable, no? So I think you're familiar with when I say it's stable system and unstable system. Okay? So So I'll read this one. No? In DSP, a concept called BIBO is used to define the stability of a system. BIBO stands for bounded input, bounded output. Bounded signal is any signal which in the absolute value of the signal is never greater than some value. Okay? So that is a BIBO kind of stable system. Bounded input, bounded output. Okay, so linearity. Linearity is perhaps the most important system property, no? So, a system property wherein it obeys the superposition property. So, what is superposition property? If you're familiar with this kind of mathematics properties, superposition property is basically the combination of two system properties wherein additive property and homogeneity or scaling property. So, unsa man ang additivity property? So, from its term, a system is said to be additive if the response of a system when two or more inputs are applied together is equal to the sum of responses. So, from its term, additive, you can add two systems, okay? And homogeneity or scaling property means if the response of a system to a scaled input is the scaled version of the response, meaning homogeneity, or if it can be scaled, if the input is if the response of a system or the output is actually equivalent to the scaled input, then that is homogeneity or scaled. Now, for example, a human ear is a linear system because if a person speaks twice as loud, the ear also responds twice as much, right? So, if maghunghong ka, your ear can actually dili ka siya na nakadungog. So that there is actually a scaling property, right? So for a linearity, for linear type of system, there should be these two properties, which is the additivity, and the scaling property or the homogeneity. Okay? So this is going to be the equation for linearity. So dili na nato na isa-isa ho na. So let's proceed. LTI systems. Both linear and time invariant systems are two very important classes of systems. But real-world systems are seldom linear and time invariant in nature. So most of the practical systems are non-linear to a certain extent. Okay, so ang pasabutan na niya, most of the real-world systems can be non-linear. Okay? However, more often than not, we model real-world systems as linear time invariant systems or LTI. No, dili sila totally linear, but they are most likely linear time invariant systems. This is because analyzing and finding solutions to non-linear time variant systems are extremely difficult and time-consuming. But if the presence of certain non-linearity is negligible, meaning ana, and if there are kanang mga negligible nga mga instances, no, not it will not affect the system badly and can be treated as linear by making assumption and approximation. So an example for that one is ato tanawon kung naba example, so wala na siya naghatag og example, no. So an example of a certain kind when we say linear time variant systems. So an example of a linear time variant system is is the is any electrical circuit consisting of resistors, capacitors, inductors, and linear amplifiers. Okay, so nga naman, this is a good example for an LTI system. So kung basahon nato balik no ang LTI system. So balik ko na tog basa unsa man jud ang LTI system. So an LTI system is actually linear and time linear and time invariant, no, mo na siya nga system where if there are actually um, non-linearity it can be negligible. So when you say circuits, no, consisting of resistors, capacitors, nga na, there are really actually few to at a certain degree nga naa siya yung mga um, um, negligible nga mga differences. Okay, so that means it cannot really affect the system, no, per se. Kay example, your resistor, it's supposed to be like 2 or 1 kilo ohm, but actually na siya gamay nga error, dili siya mabot gyud og 1,000, like 950 ohms lang gyud siya. But those kind of limitations in our circuit can be negligible, and still what you want to obtain from that circuit, like kung unsa nga klase ang imong output nga gusto, can still be can still be makuha gyapon na nimo na siya nga that kind of output. Okay, so you can just have assumptions and approximations, depende, no? So with that one, I'm going to end our chapter 2, and I will be uploading the 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 third chapter in our use step. And please answer a definition type of quiz in use step. Okay, so with that one, I hope you learned something from this discussion, and I hope you have a good rest of the day. Okay, thank you so much for listening, and have a good evening. Thank you so much.